I've had several of you ask me questions about this Z-score. I would like to give you a little bit more information about what it is and how to use it. Some good news, bad news. I mean, the Z-score back in the bad old days, meaning before we had computers that could easily calculate probabilities given any distribution, we were always trying to massage things into the normal distributions format. Now, is it because we thought everything was normally distributed? Absolutely not. What it was all about was the tables that gave probabilities were the easiest to carry with you if a distribution was distributed normally. So we could take any distribution that existed and we could transform it into its standard normal equivalent form and do some calculations. So what is this transformation? Any random variable x, which hopefully you remember, I'm not sure if we've actually introduced it yet or not, is just a collection of objects, usually in some sort of real valued scale. And I would refer to object I as x sub I, and x bar is the mean of the distribution that x sub I was taken from. And sigma was the standard deviation of the distribution where x sub I was taken from. So the transformation took this number x sub I, and the numerator here says how far away is the number I'm looking at from the mean of this distribution. So that's what the numerator is telling me. Well, what's the denominator doing? The denominator is rescaling that distance. It's rescaling that distance by the standard deviation. So when I'm done, the variable z sub I is telling me how many standard deviations object x sub I is from the mean of the data. Now, if I know that, I can take a quick glance at something like the Chebyshev rule or the empirical rule, and I can get a feel for the probability. You know, what's the likelihood that I'm seeing something that is 3 standard deviations away from the mean? Not very likely. So I can do that just using the empirical rule. Now later, we will be using this object z when we're calculating something called a confidence interval, and then right after that we go into something called hypothesis testing. For right now, let's look at this table, table 1, and let's look. Here are some measures of a random variable x. I actually chose them from something that had a mean of 27.5 and a standard deviation of 3.46. So I transformed 30.9 to a z equivalent, which was 0.99. So here's what I can say. In the distribution with the mean 27.5 and standard deviation 3.46, the number 30.1 is approximately 1 standard deviation away from the mean. The value 27.9 is about 0.13 standard deviations from the mean. So this one is pretty close. And this one's not that far either. And notice this one is 0.27 to the left of the mean. So still less than 1 standard deviation from the mean. Well, this one is to the right. I'm looking at the sign of the mean, and it's about 1.7 standard deviation. So now I'm getting out to things that are just a little bit less likely. Well, could I compare the original distribution to this transformed distribution? And the answer is obviously yes. So I can look, the original distribution is this green distribution over here. Its transformed distribution is this red one over here. So what can I say? Well, it looks like the bulk of the data over here is within 1 standard deviation of the mean, as we would expect, right? 68% of all the data I would expect to be less than 1 standard deviation from the mean. And then I fan out, 95% of all the data is within 2 standard deviations of the mean, and so on and so forth. So we don't have to do these transformations anymore for lack of being able to compute compute. And the tables, which I included one down here, while they can still be used to help me calculate probabilities, they're also not particularly useful anymore. But knowing how many standard deviations away from the mean a number is can help me use Chebyshev or the empirical rule and quickly get a feel for how spread out my data is. So I hope you find this helpful. If you need something more specific, you're going to have to let me know. Thank you.